also take the time now to thank you for inviting me. Really happy to be here. First time for me at the University of Frankfurt, even though I'm actually born in Frankfurt. So. Happy. So let's remind us what we want to do. So we want to do another proof of Bezo's theorem in broken bit using tropical curves, but we already established that what we try to do doesn't work. So we need more information. Why was that? Well, we've seen, for example, that if I had a polynomial in here, this gave rise to tropical curve. For example, well, we wrote this like this: j tilde t x I. So, for example, we have this very easy example of a polynomial of degree 1, a 0, 0, x out 0, not like a 1, 0, x a 1. Right, so something like degree 1 gave rise to a tropical line that's like this. The lowest exponent of my Clouseau series coefficient here, pretty much just tell me where this one is, where the origin is, but I completely lose this information. But later we want to compute some determinant of the Jacobian where one of the polynomials could be of the form like this, or like this, or the form like this, up to this. And we want to know this up to squares, but certainly up to squares we need to remember some coefficients, but we've seen that up to squares this was just the units of k, what the units of k squared. So if I have something like this, I can, which let's say starts with just the same thing, to the times t to some lowest exponent, which was minus the valuation of higher order terms, we just send it to the initial. So we want to remember these initials, and that's the definition we're going to use for the enriched tropical curve. We want to remember all three initials here. Let's use this notation. So I write the A00, which is the initial of this one here, the initial coefficient. Here I write A10, here I write A01. We want to remember these three. Yeah. Alternatively, I could attach them to the dual subdivision, which is very simple here. So to each vertex here.
Just a question concerning notation. This is the same as a tilde 00, or?
Yeah, I should write this out. That's right. I to the t, and t to the minus the variation of a
Okay.
tilde t
Right.
plus higher order.
Thanks.
So that's the information we need to remember. So in general, if we just want to state the result for tropical curves, we want to call these enriched tropical curves. So this, as I already said earlier, that first this is really inspired by Berkeley, who instead of having these coefficients here, which we only need to know them up to squares, he had pluses and minuses. So also this is also worked used in the Panamatic campaign. And for straw, Andrés mentioned this earlier, they redid the count of bi-type tangents to a quartic, plain quartic, and they also use this definition, and finally by Andrés. So enriched, call this enriched tropical curve, is this tropical curve. Together with coefficients. I also want to make this a definition of coefficients. A in here. Assigned to each component. Or assigned to each connected component. So let's say the top of the curve is called C. R2 minus and R2 minus C. Or alternatively, the vertex and the dual subdivision. So, right. Also want to make another definition. If I have something like this, if I have a tropical curve like this here, with coefficients for each of these components, I can also get something like an equation like this back. I can recover this equation back. Not quite. I only know the initials here, and some exponents here, but these of course differ by scale. But let's call this enriched. And enriched. Let's call this enriched zero equation. Or enriched tropical curve. Is of the following form. We have a polynomial, we have aij. These are not now really elements here, just in k, units of k, x to the I, y to the j, t to the exponent, and such that if I take the variation, this variation gives me back the enriched tropical curve. And so if I have an enriched tropical curve with coefficients like this, I can find a piecewise linear function. I guess you know all this. And I can attach a polynomial like this, but now I also have to, here I have coefficients that describe them in front of the corresponding polynomial, so I can go back. And later we will take these equations to define our multiplicity. But okay, let's we wanted to do Bezout, so let's recall what Bezout's theorem for tropical curves looks like. So let me say classically, because we now let's first do it without so one very nice and easy proof for Bezout's theorem of tropical curve. Of course, the Bezout's theorem for tropical curves tells me that again I get the number of intersection points is the product of the degree. So here I only consider tropical curve with Newton point from delta V, which is the convex hull. These 3 points. This. And then Bezout's theorem tells me that the sum of intersection multiplicities is the product of the degrees, or of these things. Okay, let's look at an example. So for an intersection of two tropical curves, or an intersection point of the two tropical curves. Little key example, and just intersecting, let's say, conic with a line, and I want to look at the dual subdivision of this, which I draw in colors according to the colors I chose for my curves. And I'm missing out this one here. Then an intersection point here we can observe. So the union of two tropical curves here, just through the union of two tropical curves, is a tropical curve again. In the dual subdivision of the union, this corresponds to a parallelogram. In the dual subdivision of the union of two tropical curves, T1 and T2. And subdivision of the union. And then you can define an intersection multiplicity at this intersection point to be the following. Just the area of this parallelogram towards it. Maybe you've seen another definition, but this is equivalent to this. This is a good definition, and for this definition, the proof of Jesus theorem, which I want to call now, gets very easy. Now, I need to zoom the tropical curve. Which, if I'm not mistaken, goes back to Bernd Stuhlfels. And it's, of course, says that for two tropical curves, C1 and C2, it's Newton polygon. Delta D1 and delta D2. This also works in the more general setting, and then we'll get the mixed volume, but okay, let's do the easy setting. The sum over all intersection points over the multiplicities C1 of P and C1 and C2 equals the product of 1 plus 2. I can express my sum in a different way. Follows sum section multiplicities 2. Effective C2. I claim get the picture. It's just the sum of these parallelograms. And this easy picture is just the sum of these two, the areas of these two parallelograms. But I want to compute this in a different way. I first take the big triangle area, D1 plus D2, and I subtract delta D1, which is just this guy here. And I subtract delta D2, which you get by putting this part down here and this orange part down there. Yeah. Delta D2. What is this? This is the math. It's D1 plus D2 divided by 2 squared divided by 2 minus D1 squared divided by 2, 2 squared divided by 2. And now, what do you get? It's you will get 2D1 times D2 over 2, which is 51. And this is the proof we want to generalize later, which Andrés will generalize that. But okay, in order to generalize this proof, we need a bit more information in our section. It should be quadratic form, and we also know what quadratic form it should be. It should be the determinant of the Jacobian of our polynomials defining our curve for the Puiseux series. Or we've seen we only need the initial, so we only need something of this one. So we could also start with the two enriched popular curves, assign an equation like this because we only care about these initials. And then we just compute the determinant of the Jacobian evaluated at 0 of these two. Well, everybody got any questions? And like I usually give these talks to people who don't do tropical geography, so I introduce all kinds of notions like dual subdivisions of P0. So yeah, but I probably you don't know all of this. Yeah.
It doesn't mean you don't have to.
Ah, okay. Well, I didn't do this yet. But yeah, I don't know. Dual subdivision is to have a tropical curve and you subdivide the Newton polygon, which is the convex hull of the exponents. Wow, this is this delta D1 plus D2 here. One way you could do this is you just draw an orthogonal line to each edge. So the edges are orthogonal to each other. One determines the other, at least the combinatorial of the other. There was maybe more confusing. Okay. How can we define the enriched intersection multiplicity? That's definition of the enriched intersection. So let's give it our definition. Let T1 and T2 to enrich from the curves. That means that we have these coefficients to each component or to each vertex in the subdivision assigned, and let's assign also some of these enriched view equations. So that F1 can write it as a ij to the I, y to the j, t to the ij, and say pij, x to the I, y to the j, t to the, let's say, alpha ij, where these Aij, Bij, with units of basically K, that these let's say associated enriched viewer equation. What we mean by this, well, if I take the valuation and remember these coefficients, I get my enriched tropical curve back. But these are not unique. These exponents you could shift, but in the end it doesn't matter for the definition. Then we define the enriched intersection multiplicity at an intersection point P of my enriched tropical curves to be the following. I have to take the determinant of the Jacobian of these two equations. But do I want to evaluate them at what I call this B, and I have to take some trace. In priori, but here, if we've already seen that this is just what is all this here? So Z is a point in my in the plane philosophy series that tropicalizes or such that the variation of P back and E is the K-algebra. So this would be a finite K-algebra, defined by all of these. All such C. It doesn't matter which C we pick. The information is all contained in the trace. So this will turn into the sum of generators over all of these different. This is really the definition we've seen before. And we want to define our intersection multiplicity like this and see what happens combinatorially. And I'll state our main theorem and tell you what this is. I mean, the proof of the theorem I won't do. It's just really doing the algebra and being clever. So, theorem is the following, namely that this intersection enrichment intersection multiplicity, then just in combinatorial terms, is the following. So we see that this point little p corresponds, so this like this one here is little p. This corresponds to a parallelogram here. And we again want to express our multiplicity in terms of this parallelogram when we do subdivision. So we sum up over the vertices of P. Here P is dual to this intersection point little p, intersection of two enriched tropical curves. But we don't sum up over all the p's, the b's, all the vertices, only over the ones with both entries on. So all of these vertices here are lattice points. So I can look at them not too, and we're only interested in the odd ones. What do we sum up over? We have the coefficient of p. So I said that an enriched tropical curve. I guess I erase this. Was a tropical curve such that to each component I have a coefficient assigned, or alternatively to each vertex in the dual subdivision I have a coefficient assigned. That's exactly this coefficient. AB is the coefficient of the vertex B. And I have to remember a sign, which depends on B and the parallelogram. So this is equal to plus or minus 1. Epsilon P B equals either plus or minus 1. That's really in which way the tropical curves, that encodes in which way the tropical curves intersect. So this is if C1 comes first, then C2, I'll tell you in a second what first means. C2 comes first, and then C1 if when walking around the vertex V in P. Okay, I'm almost done. The thing is, we might have not have a big enough quadratic form. In the end, we want a quadratic form of the size, so on a vector space of dimension, the area of the dual parallelogram here. If we want to do have k the complex numbers, this is just the integers, and we wanted to get this back. This might be too small. So we have to add the correct number of hyperbolic chords. So I take the area of 8p, I subtract the number of vertices which such that both components are odd. I divide this by 2 and I multiply this by the hyperbolic form. Okay, let me in the last minute finish. Maybe let's just look at this example. So we want to now do the enriched count. So we need coefficients assigned to each vertex. Actually, we don't. It suffices to tell you to know what the coefficient at this vertex is. Let me call this A, B. Why is that? This is the only vertex we're interested in. That's the only vertex with one, which is odd in both components. This is 0, this is 1, 1. I mean, this is, yeah, just check it. Like, this is the only, in this little picture, this is the only vertex we're interested in. I should order my curves, let's say. The orange one here is C1, and the white one is C2. So now, anti-clockwise. Depends on which direction. In the end, it's just same as everything right side, so it doesn't matter. So let's walk in this one here, anti-clockwise. So I walk like this around B inside of here. So first comes C1, then C2. So here, the multiplicity at P is first C1, then C2. So it's plus AB. Let's maybe also do the other one. Let's call this Q. It's only a little q. Then the multiplicity at Q. What is this? We again only care about this one vertex. We walk around here anti-clockwise. So first comes this the white one, then comes the orange one. So first C2, then C1. So this is a minus sign. So this is minus AB. Now you can see the the first case where the Zoom theorem holds, then sum up all of these intersectional pieces. I don't have enough space, so I sum up these two. What do I get? It's AB plus A minus AB. So if we remember what Zoom's theorem over said, it was always a multiple of the hyperbolic form. So if there's a multiple of this hyperbolic form, now I have to remind you of the relation 3 in about what Andrés told you, which was the following: A plus minus A is always 1 plus minus 1, which is a hyperbolic form. So this is actually a hyperbolic form. And this example easily generalizes to proof of Zoom's theorem, but that Andrés is going to tell you about. Are there any questions?
Did you figure out that this is the multiplicity that you want? This multiplicity tilde equals to distinguish 3 terms.
Yeah, so here's by definition. You do this algebra and look at the picture, what happens to the picture.
Okay.
And especially we look at the dual subdivision, because that's where the proof of the proof I presented to you happened. And we just stare at it and to look at what coefficients are important. That was really hard to figure out, actually. Like, first it was just a mess. And then we see, oh, it's actually only these coefficients where we have the vertex has both components of this follow from our algebra. And then it was not so hard to figure out the sign rule. Yeah. But yeah, the theorem is we calculate this and then we get this. Oh, I understood the question.
Yes.
Okay, good.
Okay. There's also a question in the chat. Please speak up. You have to unmute yourself.
Sorry. Yeah, I'm wondering if you can explain again why the multiplicity is independent from the order of C1 and C2.
I mean, it's not. You get the minus sign. It is. You really have to make a choice.
So multiplicity of C1 comma C2 would be different from the multiplicity of C2 comma C1.
Exactly. You would just get the minus sign inside the bracket.
I see.
But this is also the case. I mean, this is also the case for algebraic curves. It really depends on which way you want to intersect them. So that's really what it should be. And in the end, the sum, because of this relation, will get this. Yeah. Thanks for the question. That's a good point.
Thanks.
As we said that we can to prove this, and we can use the definition. So it's here. The comments about it. So the first comment is that we did this not only for curves, but in general, this definition, proper definition, can be extended, right? So you have now tropical and tropical hypersurfaces, right? So we want to begin that intersect tropical transversely. So we're going to have the section that is in the middle of two-dimensional faces, we're going to fit, and this is where the sum is the same. Only 5 vertices of sine given by the sine of the frame, the sine of the frame with the out case. So the dual to this is going to be, I'll repeat it, sorry. And so this is my vertex, and I have that this vertex that generates the polytope as we can see, it will give me an a kind of Rn. I can state the sign of this. It will be sine times the product of the coefficients that come from the enriched device. Yes, and then our proofs of the first things to do, at least for curves, is if we need to what we need to do is calculate the trace of the Jacobian of your functions of your polynomials, right? So this actually using the remark that Andrés made, right? So at least for the kinds of curves, right? So we have two curves here. We have that around this point we have a local definition. So here the maximum of, at least for if this is C1, let's say the maximum is made with a monomial. Let's say alpha I is to the I. This is I1, I2, right? And then from the same curve, we know that the maximum here is in a different monomial, prime, prime, where along this line, the maximum is obtained twice in this. So this actually, all these equations can be reduced because we aim to take the initial, right? In this case, they will have 5, and for this at this point, what we need to trace down.
So the brackets basically can take the initial for you.
Yeah, if I take the initial inside the bracket, right? If I need to take the initial of a determinant, right?
Yeah.
Yeah, so I can just derive, and then if what happened, if I'll say like the coefficient of the expected valuation is not zero, then that is the initial, right? Yeah, then we calculate that one, and then this is get is the area of the other times a sign that comes from yeah, basically the determinant of how we put the equations, and then we get the coefficients, and we get, well, without initial we get this set, but then now we get the initial error is set, and then this is because this coefficient delta I delta j minus 1 for delta I is 9 and the j where those are the ones for C2. This is for the model delta j is j and beta j prime. So that's the whole point of this. The K algebra defined this solution is what we like creates an algebraic extension, and then when you trace down, you get exactly yeah, what we indicated before, and yeah, by tracing down these up to squares, we realize that there's and so the only terms that doesn't come to the solid are exactly these points. Now let me say this theory with a little bit more of a generosity. So So we also, if we see, this is a strictly local situation. So it's unrelated to the fact that we're intercepting curves on P2 or the curves that have delta. So let me put it here. And then an example now for the curves. So if we take and enrich surfaces, well, tropical lectures over surfaces in Rn. Then we get that this product defines the sum over all the intersections of the tropical subjacent varieties of this principle. This is going to correspond to the mixed volume of the degrees minus an error there times h plus 4 quadratic forms of lengths L. Well, this L corresponds to the number of points in the boundary. So I take the boundary, this sum of the degrees, and then I consider the odd points. And then this is this L. Okay. So this specializes to theory. So when every di is different size, the standard simplex, then this formula is the two formula. The enriched key, right? And this formula, well, I mean, if we try to calculate this all, because the two formula is only for orientable cases. So this is going to be odd. So L is going to be 0 if I have that the sum of the i's. Right. So let me give a proof of this for the case of curves. I can say a work to realize this. Okay, so how do we prove it? So we prove it first for curves, and then we use this to solve this dimension. So the curve, just look at the odd points, so we're going to change, right? So we are trying to sum over the intersection. Things is enriched multiplicity. We know that the enriched multiplicity is the sum over the odd vertices. So what I can do is the sum over all of vertices of sigma, the contribution that corresponds to this. So if I have a knot vertex interior, right? I got the phenomenon that's happening here is going to be a constant phenomenon. So I'm going to remind that we're going to have, so for B in the interior, we're going to have an even number of elements. Such that B is contained. So are the parallelograms neighboring to this one? They come in pairs. So and the alternating signs. So I have basically this can be seen better in the dual of the dual. So including the intersection. So the intersection of the two curves is going to look like this, right? So this is P, and then the vector B is going to correspond to a connected component, right? So actually, this one here, this is the dual of the vertex, right? So in these connected components, seems I assume that the intersection was transversal, tropically transversal. It means that at some point, I mean, I have to have another intersection, right? Basically, I just follow a curve, right? I follow a color, and no matter what it is, at some point you have to intersect again. And since the intersection is transversal, then it may happen that it somehow does this, right? And then it may go back to white, but then you have to. So the number of changes have to be even, and then they have to alternate signs. That means that the intersection in any of vertex is going to be an let's say, well, a number is a multiple of H. Right. Again, for the condition that Sabrina mentioned, so I was going to have the coefficient that corresponds to the vertex that is fixed, does not depend, and an alternating sum of this. So this is just a sum of H. So I know the shape of this thing, and I know that the rank of this sum, right? So the rank is of the sum is the sum of the rank, the parts, and then this recovers the complex part. So for this, in one stage. And then for the hypersurface case here, right, we're going to consider the same. So an odd vertex now in an odd vertex is gonna have a number of parallelograms that gets close to it. So adjacent to it. And then you see now that the alternating sign property, what we do is we look at the first intersection, the n-1 of the intersection of the n-1 first varieties. This is a tropical curve. And then we have the cyclical. And then following, along this tropical curve, we have similar arguments too. They come with pairs and they have alternating signs. Okay, so that is for in the interior. Now what happens if I have a vertex that is in the boundary? Okay. So now if I have a vertex in the boundary of the dual polydot, that means that the region dual to it is not bounded. So I can have something like this, where we have this is the dual V. That means that when I consider D in the dual subdivision and of vertex, I may have a number of parallelograms that is still alternating, but I don't have an even number. So whatever contribution it is, right, is going to be a multiple of H plus one of these error forms. And then I have as many as of vertices in the bundle. Okay. So let's make a picture of the for now. So now let me give an example of discount for something that is not the projected plane. So let's consider now curves in P1. Okay. In this case, if I have two, they have degree. The degree are going to be rectangles of base A and I B prime B respectively. And now if we try to compute the intersection, so now we have C1 times C2. This is going to be the mixed volume of these two, which is A B prime plus A prime B divided by 2H minus L H plus A1 L. So now let's look at when can we how do we calculate this L, let's say, and how we made that this error to be a multiple of H fails. So what are the points in the Minkowski sum? So for this, the Minkowski sum, right? So this rectangle of area of flat sides A plus A prime and B plus B prime, right? So when this social rectangle doesn't have all points in the boundary. So for that, I just need that a plus a prime is 2, and the difference is 1. So this is, let's say, the tropical version of it. But now if I try to go to the right side, if I consider really curves there and P1 cross P1, right, I can still go back to my original setting. What happens if I have this vector bundle on P1 cross P1 given by A times B, A times horizontal plus B times vertical. Right. Then when is this vector bundle orientable? So remember that the determinant of this vector bundle times the canonical of P1 squared needs to be a square, right? So we calculate this, then we got OP1 squared of exactly the determinant of B, which is this OP1 of the sum, minus, no, well, times the canonical of P1 squared, which is minus 2h minus 2. So this is a plus a prime minus 2h plus b prime minus 2. Right? So this is orientable. If and only if, well, these and these are even, but I already did this, and then I can just write it as L equal to 0. Right? And then this actually translate in all the examples that we know. So we can also write this down, for example, for the huge resurfaces, right? So we would write down the tetrahedron that corresponds to it. And then we see that the orientability condition translate into a combinatorial one. So the vector bundle of the algebraic curve that you consider is orientable if and only if L is equal to 0. So we have looked into that. And then we have found that in the example that we know how to calculate it, it all happens. So we have the question of when can we find, or how to find a good example, or what can we do with it? So let's say that a third variety X satisfies the orientability combinatorial orientability condition. If for every family of n by bundle, where n is the dimension of x, right? We have that the direct sum of I is orientable if and only if boundary of the Minkowski sum of degrees doesn't have points, right? So we can check that for Pn and for P1 cross P1 it's true, but as I said before, for the Husserl surfaces, it's true. For blown out points of P2 is true. So all the example is true, and we also have theorem. This property this goes in the product. Meaning that if I have X and Y to third variety that satisfy this combinatorial orientability condition, then the product does it, and this is just because the line bundles for on a product they can be decomposed as tensor product of line bundles over the base. Yeah, and then, well, I mean, we would like to know, or is an open question of if this is always true. So every third variety where we can do a small third variety, we can apply this tropical approach, will satisfy this condition. This is what we wanted to say.